Welcome to the Week 5 video for BY 245. This week we're going to focus on identifying or diving into how to spot pseudoscience and what role the media can play in perpetuating inaccurate information about science. We will then focus on why science needs statistics. So first, if we think about the word pseudoscience, pseudo means fake. So how can we identify fake science? Well, knowing as much as possible about the real thing is the first step, meaning knowing as much as possible about science itself makes it easier to identify when something isn't real science. We must clearly understand science itself. As you recall, science is not simply knowing scientific facts, like the distance from the Earth to the Sun, the age of the Earth, the distinction between mammals and reptiles, etc. Science requires valid evidence and has set criteria for what that means. Controlled experimentation is necessary. We weigh all possibilities when possible, test hypotheses, establish meaningful theories, and most importantly, is to draw reliable and accurate conclusions. And so it's really important to know the limitations of science. As you know, the media provides a continuous bombardment of sheer nonsense, misinformation, fantasy, and confusion, all proclaiming to be true facts. Sifting sense from nonsense can be an overwhelming job, particularly in this time when people spend copious amounts of time consuming media content. In fact, more than ever before, time is spent consuming media online. How does the media aid in the spread of misinformation? As people pursue their social media content, reading headlines only is their primary source of news many times. I'm sure you've experienced this yourself. Remember the Ebola scare? Here is an example of 3 respectable news sources, respectable to different groups, of course, but still seen as somewhat reputable, reporting on the same story related to a doctor in New York who tested positive for Ebola. What these headlines failed to include are the facts that this doctor posed zero threat to the public, as the doctor was quarantined prior to being contagious. Alone, these misleading headlines lead immediately to the spread of false information and fear among the public. The "we are all going to die" idea spreads quickly, and blame is placed where there is no reason for blame. As you can see from the headlines, what's written in red under each one are simple things that could have been added that could have changed the way that people read and thought about this story, and could have led to a lot less public scare or fear. But this is all the spread of misleading information, likely balanced on a priority to increase sales and/or circulation of their media source. It keeps the story going for longer than it probably should. But what about false science and media? Here's one example, the detox diet, and it's promoted by Dr. Oz, of course. Here are some images that I found online that tell you how a detox diet can cleanse your body. They can eliminate sugar cravings, kick the caffeine habit, boost your metabolism. My favorite one is clean out your liver, boost your brain clarity, kickstart weight loss. The 100 best detox diets of all time. They include salads, soups, drinks, and snacks. And then, of course, you have Dr. Oz promoting the detox food craze that will help you lose 10 pounds. So the media plays several roles in pushing pseudoscience, whether they intend to or not. Take these 2 examples. The first one that claims to identify the myths of detox diets was published on the New York State Public Media news site. And it focuses slightly on the bogus notion that diets can detoxify, in quotes, your body. This story was on the local NPR radio station and then posted on their website, WRVO's website. The article actually spends more time on the negative consequences that detox diets can have, instead of just focusing on the bogus notion that diets can detoxify your body and how your body already has a detoxification system in your liver and kidneys. It doesn't explain how the word toxin is misused by these diet claims. Another thing is, even though there is quite a bit of good information in this particular piece, another thing is where this particular media source finds itself on national public media. Now, of course, there's nothing wrong with that. We'll get to that in just a second. If you would like to listen to the original airing of the NPR segment on the myths of detox diets, I've posted a short video clip on Canvas to where you can go listen to that. All right, so let's talk about the platform that this particular piece on detoxifying diets is found and what the audience profiles look like. Across all national public media platforms, National Public Radio reaches the nation's quote-unquote best and brightest. The NPR audience is influential and curious and well-connected to the top business managers and executives, as well as the most highly educated. Looking just at audience profiles of National Public Radio based on lifelong learning as a metric, NPR listeners are 240% more likely to have a postgraduate degree, 28% are more likely to be in graduate school, 456% more likely to have a doctoral degree, and 52% have at least a college degree. So the average American is not necessarily covered by this media outlet. The second article here is on CNN. CNN has a much more broad audience profile and reaches a much larger average American audience. So what insight into the pseudoscience of detox diets does this article offer? First, there's a brief paragraph on the negative effects of detox diets, and then the article goes on to explain how there is a sustainable detox that is worthwhile and gives directions to how you can do this detox. Quote, "If you read about the latest wellness trends, you may have entertained the idea of a detox diet. But whether you've considered juicing, fasting, or cleansing in an effort to lose weight or improve your well-being, you're probably aware that drastically cutting out foods is not effective as a long-term lifestyle approach to healthy eating. In fact, strict detoxing can cause issues including fatigue, dizziness, and low blood sugar." And this is where it turns away from the idea of detox being a pseudoscience and telling the audience that there are ways that you could do this okay. Starting at here, but there is one kind of sustainable detox that is worthwhile, according to some experts. Reducing sugar in your diet can help you drop pounds, improve your health, and even give you more radiant skin. End quote. So what are the issues with this main popular media outlet in this article relating to the pseudoscience of detox diets? Well, first of all, the use of the word toxin. As the diets offer to serve as a detoxification to remove toxins from your body. In science, a toxin is generally defined as substances created by plants, animals, and microorganisms that are poisonous to humans. Some medications can also be toxic in large amounts. However, this mainstream phenomena of detoxification has effectively made this definition meaningless. For example, detox plans variously refer to refined sugar, caffeine, red meat, alcohol, gluten, and a host of environmental contaminants as quote-unquote toxins, and cite conditions as varied as obesity, fatigue, skin rashes, joint pain, congestion, insomnia, depression, bloating, and cancers as evidence of toxicity in the body. Much detox lore is focused on the colon, where the lore states that toxic substances supposedly attach to and fester in the colon's lining, increasing the risk of illness unless they're removed through a special diet or, in some cases, enemas or colonic irrigation. I want to point out that both of these notions are false and even somewhat absurd. Your fecal material does not harbor toxins that can make you ill, and cleansing your colon is unnecessary at best and dangerous at worst. The only reason to undergo colonic irrigation is in prepping for surgery or endoscopy. In fact, colonic irrigation can lead to serious complications, including severe diarrhea, life-threatening blood infections like septicemia, and or perforation of the intestinal wall. The facts about detox diets' pseudoscience status include that the human body itself is a marvelously efficient detoxifying machine. The skin, the body's largest organ, serves as a protective barrier against harmful substances. Your airways trap and expel bad particles. Your intestines screen out parasites and other harmful organisms while allowing nutrients to be absorbed into the blood. The liver acts as your body's primary filter, responsible for aiding and digesting food and ridding the body of toxic substances. Your kidneys also filter out toxins through the production of urine. All of these organs work in concert with the immune system to keep you healthy. Healthful eating, sleeping, and exercise habits will keep the machine running optimally. Substandard ones will compromise it. There is zero scientific evidence that a special detox diet or fast can take the place of or supplement what your own body is naturally programmed to do. So how do we identify pseudoscience? There are some clear earmarks of pseudoscience. The substitution of fantasy and nonsense for facts leaves behind many different clues and signs that almost anyone can readily detect. Here, I will give you some of the most common characteristics of pseudoscience, where the presence of any one or more of these symptoms in any material in question marks it conclusively as pseudoscience. However, material displaying none of these flaws might still also be pseudoscience. These are flaws that are sufficient rather than necessary conditions for pseudoscience. The first one is that pseudoscience is the indifference to fact that pseudoscience holds. So pseudoscience displays a remarkable and characteristic indifference to fact. When there are made-up bogus facts, instead of going to the trouble of consulting reliable reference works or investigating anything directly. These fictitious facts are often central to the pseudoscientist argument and conclusions. And pseudoscientists never revise their stance. The first edition of any pseudoscience book is almost always the last one. The pseudoscientist moves on to another claim quickly, unlike college textbooks, like science textbooks, which have new editions every few years to update them with new facts, ideas, discoveries, experiments, and insights. A good example of the remarkable characteristic of indifferent to facts is the detox diets, that they remove toxins from your body that cause disease. There's no evidence that supports this, and this idea is extremely characteristic of having indifference to fact because of the way it defines toxins, and we'll come back to definitions in a little bit. It's more of a trust me kind of idea. Pseudoscience includes quote-unquote research that is almost always invariably exegesis. So what is exegesis? It's an interpretation of something based solely on face value, much like the way that religious texts are interpreted. Pseudoscientists often clip newspaper reports, collect hearsay and questionable memories, and read other pseudoscience books, or thumb through ancient religious or mythological works. They never or rarely ever make an independent investigation to check sources, and sources are taken at face value or even interpreted as symbolic, reading into the myths and old text anything that they would like to find in them. Sometimes this appears as very simplistic literalism, like the use of inherited sacred texts as if they were contemporary science textbooks. This particular practice leads and has led to the flat earth hypothesis. Creationism falls in this same kind of spectrum of focusing on these ancient religious texts in order to make scientific or quote-unquote scientific claims, fall under pseudoscience because they're exegesis. Intelligent design is another one. Pseudoscience begins with a hypothesis that is usually appealing emotionally and is spectacularly implausible, and then looks for and includes only items that support it, while any conflicting evidence is ignored. You usually are confronted by a question that begins with, "Do you believe?" Such as, "Do you believe in ESP?" The focus is not on the evidence or if the evidence is good, but rather if you believe, generally speaking. Pseudoscience aims to rationalize strongly held beliefs rather than investigate the actual issue. Pseudoscience specializes in jumping into congenial conclusions, grinding ideological axes, appealing to preconceived ideas, and to widespread misunderstandings. The general public tends to view pseudoscientists as mavericks who are working slightly beyond the accepted boundaries of science. In fact, nothing could be further from the truth. Pseudoscientists invariably represent a worldview which is not simply unscientific or pre-scientific, but is militantly anti-scientific. Pseudoscience shows a total indifference to criteria of valid evidence. The emphasis is not on meaningful, controlled, repeatable scientific experiments, but instead the focus is on unverifiable eyewitness testimony, stories, faked footprints, blurry photos, and tall tales, hearsay, rumors, and dubious anecdotes. Genuine modern scientific literature is not cited. Real research is never conducted. Generally, there is never any valid evidence of any kind whatsoever provided for their claims. The most common tactic is to publish a novel, a work of fiction, in which essentially everything is made up by the author, and treat the made-up material as if it were actual, factual, and researched. A recent example is the Da Vinci Code, which was written by Dan Brown. When pressed, the author will sometimes point to the fact that the book is fiction, but generally, when not pressed, the authors will treat the ideas and the stories themselves as established facts and build upon them to generate more best-selling books. Pseudoscience relies heavily on subjective validation. An example: Joe puts Jell-O on his head and his headache goes away. To pseudoscience, this means Jell-O cures headaches. To science, this means nothing, since no experiment was conducted. Many things were going on when Joe's headache went away. The moon was full, a bird flew overhead, the window was open, Joe had on his red shirt, etc. And his headache would have gone away eventually, in any case, no matter what. Modine Flark reads her newspaper horoscope and says there must be something to astrology because the horoscope describes her perfectly. But when we read it, we see it is a perfectly general statement, or generally true statement that describes just about every human who has ever lived, and has nothing to do with Modine or her birth stars. These are examples of subjective validation, one of the main foundations of popular support for pseudoscience. Essentially, all of alternative medicine relies on subjective validation entirely for its continued existence. A controlled experiment to study the effectiveness of a headache remedy, for example, would put a large number, thousands or tens of thousands, of people suffering from headaches in identical circumstances, except for the presence or absence of the remedy it is desired to test, and then compare the results, which would then have some chance of being meaningful. Subjective validation renders such studies meaningless unless they follow a so-called double-blind protocol, which ensures that no one involved in the study knows what the results should be. That is, no one in the study should know until final results have been tabulated which patients took the remedy to be tested and which patients took an identical appearing placebo, known to have no effect on headaches. Pseudoscience depends on arbitrary conventions of human culture rather than on unchanging regularities of nature. For instance, the interpretations of astrology depend on the names of things, which are accidental and vary from culture to culture. If the ancients had given the name Mars to the planet we call Jupiter, and vice versa, astronomy could care less. But astrology would be totally different, because it depends solely on the cultural baggage carried by the name and has nothing to do with the physical properties of the actual planet itself. Pseudoscience always achieves a reduction to absurdity if pressured far enough. Maybe dowsers can somehow sense the presence of water or minerals under a field, but almost all claim they can dowse equally well from a map. Maybe Uri Geller is psychic, but are his powers really beamed to him on a radio link with a flying saucer from the planet Huva, as Uri used to claim? A local psychic says she can commune mentally with your pet, but she also says a photo or fax or even computer printout image of the pet works just as well as the pet itself for her communing. Pseudoscience always avoids putting its claims to a meaningful test. Pseudoscientists rarely ever carry out careful, methodical, convincing experiments themselves. And they also generally ignore results of such experiments that are carried out by scientists. There is literally no follow-up. Where a pseudoscientist claims to have done an experiment with a remarkable result, he himself or other pseudoscientists almost never repeat it to check his results and procedures. This is an extreme contrast with science, where crucial experiments are performed over and over by scientists all over the world with ever-increasing precision. When pseudoscientists became extremely excited by fuzzy 1980s photos of a face on Mars, they somehow never wanted to look at or even hear about 1990s and later photos which show the area with much sharper resolution and do not show any face. It doesn't occur to practitioners of therapeutic touch, which involves ritual hand-waving to manipulate and smooth the human energy field, to demonstrate experimentally that such a field, completely unknown to science, actually exists. Believers in the supernatural wonders of crop circles never bother to take a clothesline and a broomstick and see how simple it is to make a circle precisely like the ones they find inexplicable. Pseudoscience often contradicts itself, even in its own terms. Such logical contradictions are simply ignored or rationalized away. In a meaningful description of the physical world we live in, mathematical or factual or logical contradictions simply could not exist. In pseudoscience, they are par for the course. We should not be surprised when a book on dowsing for water, in Chapter 1, assures us that dowsers prefer newly cut twigs, as the one shown here, because only still living wood can channel and focus the earth radiation used in dowsing, while in Chapter 5 of the same book states that nearly all dowsers now use metal or plastic rods, as shown here. Pseudoscience often contradicts itself. Pseudoscience deliberately creates mystery where none exists by omitting crucial information, background, and important details. Anything can be made mysterious if you omit to tell what is known about it or present completely imaginary details. The Bermuda Triangle and Sea Mystery books are classic examples of this tactic, as are most books on haunted houses. Pseudoscience does not progress. There are fads. Pseudoscientists may switch from one fad to another, from ghosts to ESP research, from flying saucers to psychic studies, from ESP research to looking for Bigfoot. But within a given topic, there is no progress made. No new information uncovered, new theories are not forthcoming, old concepts are never modified or discarded in the light of new discoveries, since there are no new discoveries for pseudoscience. Pseudoscience persuades using misinformation, appeals to widespread belief, rhetoric, propaganda, misrepresentation, rather than presenting valid evidence, which presumably does not exist. Pseudoscience books offer examples of almost every kind of fallacy of logic and reason known to scholars, and have invented some new ones of their own. A favorite device is the non sequitur, a statement that does not logically follow from previous argument or statement. Pseudoscientists love the Galileo argument. This consists of the pseudoscientist comparing himself to Galileo and saying that just as the pseudoscientist is believed to be wrong, so Galileo was thought wrong by his contemporaries. Therefore, the pseudoscientist must be right too, just as Galileo was. Clearly, the conclusion does not follow. What is more, anyone who has ever heard of Galileo must be aware that Galileo's ideas were tested, verified, and accepted promptly by his scientific colleagues. It was the established religion which rejected Galileo's findings, preferring instead a familiar pseudoscience which Galileo's findings contradicted. Pseudoscience argues from ignorance an elementary fallacy. That is, pseudoscientists base their claims on incompleteness of information about nature, rather than what is known at present. But no claim can possibly be supported by lack of information. Advocates of intelligent design claim, without evidence, that science will never be able to understand certain features of biological systems. Really? Never is a very long time. The phrase, "science cannot explain," is extremely common in pseudoscience literature. In many cases, the fact is that science has no interest in the supposed phenomenon because there is no evidence it exists. In other cases, the scientific explanation is well known and well established, but the pseudoscientist is not aware of it or deliberately ignores it to create mystery. Could the woods be full of unknown monsters? The rivers full of unknown monsters? Zoologists don't think so. They've been there repeatedly to look, and it's their profession to find and study new animals. To the pseudoscientist, the absence of evidence for some monster is itself a kind of proof the monster exists. Pseudoscience argues from alleged exceptions, errors, anomalies, strange or paranormal events, and suspect claims, rather than from well-established regularities of nature. The experience of scientists over the past 400 years is that claims and reports which describe well-understood objects behaving in strange and incomprehensible ways tend to reduce upon investigation to deliberate frauds, honest mistakes, garbled accounts, misinterpretations, outright fabrications, and stupid blunders. It is not wise to accept such reports at face value without checking them. Pseudoscience always takes such reports as literally true without independent verification. Pseudoscience often pretends to be one side of a legitimate scientific controversy. That is, pseudoscientists like to pretend that the jury is still out and that further research is needed to clarify the validity of their beliefs. This is essentially never the case. For example, there is no controversy among astronomers concerning astrology. They unanimously agree it is nonsense. Additionally, there is no controversy among biologists regarding intelligent design. It is dismissed as a set of religious-based beliefs, empty of scientific content. There is no case known to me in which a pseudoscientist's claims have taken advantage of any genuine scientific controversy. Instead, pseudoscientists operate entirely outside of science, and their claims and beliefs are not relevant to any known scientific puzzle or uncertainty. One frightening trend observed more and more strongly during the last half of the 20th century was the incorporation of contrarian pseudoscience into the core beliefs of various fundamentalist religions, so that today a fundamentalist is almost certain to deny the facts of global warming, biological evolution, human origins, etc., and to affirm that basic scientific research is essentially of no value. There is general agreement among interested observers that, over the past 2 decades, Americans have grown increasingly indifferent to the often demonstrated fact of their ignorance of even the most basic scientific discoveries of the last 4 centuries, and increasingly unconcerned that United States K-12 students generally place poorly in knowledge of math, science, and even reading, in comparison among 70 or more nations, as shown here. An actual and naked hostility to science and scholarship has been tied up seemingly inextricably with political and religious ultra-conservatism. This attitude of distrust and dislike of science, mathematics, and rational thought in general very obviously has an entirely negative educational impact. And ultimately, such hostile attitudes must result in an ever-increasing popularity for various pseudosciences, particularly those which can adapt themselves to the prevailing political and religious dogmas. Pseudoscience appeals to false authority, to emotion, to sentiment, or to distrust of established fact in general. A high school dropout is accepted as an expert on archaeology, though he has never made any study of it. A psychoanalyst is accepted as an expert on all of human history, not to mention physics, astronomy, and mythology, though his claims are inconsistent with everything known in all 4 of those fields. Emotional appeals are common. If it makes you feel good, it must be true. In your heart, you know it's true. Follow your bliss. Use your intuition. Pseudoscientists are fond of imaginary conspiracies. There's plenty of evidence for flying saucers, but the government keeps it secret. They almost always argue from irrelevancies. Scientists don't know everything, but perhaps we weren't talking about everything. Maybe we were discussing the evidence for the tooth fairy and Santa Claus. Pseudoscience makes extraordinary claims and advances fantastic theories that are in contradiction to what is known about nature. Not only is no evidence offered that the claim is true, the problem of how all previous investigations led to precisely opposite conclusions is ignored completely. An example, quote, "This electric spark I'm making with this electrical apparatus is actually not a spark at all, but rather a supernatural manifestation of psycho-spiritual energy," end quote. Here's another one. Every human is surrounded by an impalpable aura of electromagnetic energy, the auric egg of the ancient Hindu seers, which mirrors the human's every mood and condition. And one more. This dog knows when its owner leaves her business miles away and always goes to the window right then to wait for her, because it senses the meta-human supermorphogenic force field. Gosh, what if it just goes to the window every few minutes, all day long? The very word theory is one of the most often misused words by pseudoscience. In science, we know, a theory is a detailed, quantitative description of an observed physical process of nature. For example, in physics, a theory of gravity would be a mathematically expressed law that allowed the calculation of the gravitational force in any specific given circumstance. In zoology, a theory of evolution would offer a description of a detailed, testable set of processes that result in the frequently observed origin of a new species of living thing. You can't describe a process that is not there to be described, so there is hardly any concept more alien to pseudoscience than a scientific theory. Pseudoscientists never offer theories. They usually offer retreaded mythology. Pseudoscience makes heavy use of an invented vocabulary in which the new terms introduced do not have precise or unambiguous definitions, and most have no definitions at all. The listener is forced to interpret the statements according to his or her own preconceptions. What, for instance, is biocosmic radiation energy? Or a psychotronic amplification system? Or the intelligent design hypothesis? The zero-point vacuum-free cosmic energy motor? What about craniosacral therapeutic osteopathy? By spouting gibberish that has a vaguely technical sound, the pseudoscientists believe they imitate the jargon of actual scientific and technical fields. Pseudoscientists also like to take terms from actual science, such as energy, and drain them totally of meaning, then use them as senseless, referentless buzzwords. Take the word organic, for example, the use of organic to describe vegetables. If you know anything about the scientific definition of organic, you know that that means carbon-based. So how then could you have non-organic vegetables that you would eat? Pseudoscience appeals to the truth criteria of scientific methodology, while simultaneously denying their validity. Thus, a procedurally invalid experiment, which seems to show that astrology works, is advanced by the pseudoscientist as proof that astrology is correct, while he simultaneously completely ignores any number of procedurally sound experiments that show it does not work in any way or sense. The fact that someone got away with simple magic tricks in one scientific lab is quote-unquote proof that he is a psychic Superman, while the fact that he was caught doing his tricks in several other labs is completely ignored. One ESP experiment where the researchers can be shown conclusively to have simply fabricated all of their positive results is invariably referenced as valid and convincing, whilst the many dozens of other ESP studies that gave chance results are left unmentioned. A more general example of this fallacy is often called cherry picking. There are many scientific studies being published all the time, and they vary widely in reliability and methodology. Thus, you can easily find at least one study somewhere that proves that drinking 6 or more cups of coffee a day reduces the chance of a heart attack by 60%. That using a mobile phone more than 2 hours a day reduces the chance of developing Alzheimer's disease by 60%. That eating a pound of dark chocolate per day reduces your chance of ovarian cancer by 60%. That chewing a plug of tobacco at least once per week reduces the incidence of dental caries by 60%. Or generally whatever else you want. The attitude of science is that all phenomena must be capable of being studied by anyone with the proper equipment, and that all procedurally valid studies must give consistent results. Pseudoscience explanations tend to be by scenario. That is, we are told a story, but we are told nothing else. We have no description of any possible physical process. For instance, pseudoscientist Velikovsky claimed that another planet passing near the Earth caused the Earth's spin axis to flip upside down. This is all he said. He gave no mechanisms, but the mechanism is all important because the laws of physics rule out the process as implausible. That is, the approach of another planet cannot cause a planet's spin axis to flip 180 degrees. If Velikovsky had discovered some way that one planet could flip another's spin axis, he would presumably have described the mechanism by which it could happen. The bald statement itself, without the underlying mechanism, conveys zero information at all. Again, Velikovsky says that Venus was once a comet, and this comet was spewed out of a volcano on Jupiter. Since planets in no way resemble comets, which have been known since 1950 to consist of rock, ice, snowball-like debris, and which in turn have no connection whatsoever to volcanoes, and since Jupiter is not known to have volcanoes anyway, or even a solid surface, there is no actual physical process underlying Velikovsky's assertions. He just gives us words related to one another within a sentence, but the relations are alien to the universe we actually live in, and no explanation for how these relations work or can exist is given. They are stories, but never theories. The literary genre known as science fiction has been invaluable to pseudoscience for more than 150 years. In providing fact-free scenarios which the pseudoscientists can adapt readily and which have the advantage of being already familiar to the public through use and reuse in 20th century films and television series. So far, we have discussed quite exhaustively pseudoscience without making any direct comparison with science itself. It is important to make a direct comparison feature by feature, so let's start. First, within science, the literature is written for scientists. There is peer review, and there are rigorous standards for honesty and accuracy. On the other side, pseudoscience, the literature is aimed at the general public. There's no review, no standards, no pre-review or pre-publication verification, no demand for accuracy and precision. Second, in science, reproducible, reliable results are demanded. Experiments must be precisely described so that they can be duplicated exactly or improved upon in sensitivity and volume of cases or events. On the other hand, in pseudoscience, results cannot be reproduced or verified. Studies, if any, are always so vaguely described that one can't figure out just what was actually done or how it was done. Third, in science, failures are searched for and studied closely, since incorrect theories can often make correct predictions by accident, but no correct theory will make incorrect predictions. In pseudoscience, failures are all ignored, excused, hidden, lied about, discounted, explained away, rationalized, forgotten, and even avoided at all cost. As time goes, more and more is learned about the physical processes under study. This defines science. It means that scientific information is sort of fluid, where we're adding to it all the time as new evidence and understanding comes to play. In pseudoscience, however, no actual physical phenomena or processes are ever found, noticed, or studied. No progress is made. Nothing concrete is ever learned. 5. In science, individual defects, idiosyncrasies, and blunders of investigators average out. They do not affect the real signal under the study. However, in pseudoscience, individual defects, idiosyncrasies, and blunders of investigators provide the only signals ever seen. The average across these is 0. 6. Science convinces by appeal to the evidence, by arguments based upon logical and/or mathematical reasoning, by making the best case the data permit. When new evidence contradicts old ideas, they are abundant. On the other side, in pseudoscience, pseudoscience convinces by appeal to faith and belief. Pseudoscience is in almost every case, has a very strong quasi-religious element. It tries to convert, not to convince. You are to believe in spite of the facts, not because of them. The original idea is never abandoned, whatever the evidence. And lastly, within science, there are no conflicts of interest. The scientist has no personal financial stake in any specific outcome of his studies. This is very different from so-called junk science, where the self-proclaimed scientist is in fact a paid employee or paid only when he testifies to the right result. In pseudoscience, there are extreme conflicts of interest. The pseudoscientist generally earns some or all of his living by selling pseudoscientific services, example, horoscopes, predictions, instruction in developing paranormal powers, popular press books about diets, things that have no evidence supporting them. So hopefully by now you have a good idea of how to separate the real science from the fake science, or what the difference between science and pseudoscience is. No matter what, as humans, our instincts lead us astray when dealing with probabilities, and we are easily taken in by emotional appeals. We tend to jump to conclusions, even if they are based upon our own observations. For example, a 3-year-old girl told her male buddy, "You can't be a doctor. Only girls can become doctors." To her, this statement made complete sense because the 3 doctors she had ever interacted with and know in her life were all women. We also tend to be overconfident. For example, how good are you at knowing how sure you are? Let's take a minute to do a little exercise. And make sure you go through this because it'll teach you a valuable lesson about how overconfident we all are in our information. Answer each of the questions here with a range that you think has a 90% chance of containing the correct answer. Now don't cheat and use Google or other sources to find the answer. That defeats the purpose of the exercise. Don't give up and don't say that you don't know the answer. Of course you won't know the answer precisely. That is the point. The goal is not to provide precise answers, but to qualify your level of uncertainty and come up with ranges of values that you think are 90% likely to include the true answer. If you really have no idea or no clue what the answer is, then answer with a very wide interval. For example, if you have no idea what the answer to question 1 is, use a range like 0 to 120, and you can be 100% sure it includes the correct answer. Go ahead, stop the video for a minute and write down your predicted ranges for all 10 of the questions. Again, take this seriously because it'll help you with the rest of this class. If you answered 90% confidence, then you could expect 9 of your intervals to include the correct answer and 1 to exclude it. Let's go ahead and check your answers. You can pause the video here to look and see how you did. When testing this on 1,000 people, scientists found that 99% of people were overconfident. The goal of this exercise was to create ranges that included the correct answer 90% of the time. But most people create narrow ranges that include the answer only 30 to 60% of the time. Even studies of experts estimating facts in their own areas of expertise lead to similar overconfident results. How did you do? You probably fell somewhere in that 30 to 60% range. And this is why scientists use statistical methods to quantify confidence properly, as we as humans do a really poor job because we're very overconfident in our own knowledge. This table presents simulated data from 10 basketball players, 1 per row, shooting 32 baskets each. An X in the box represents a successful shot. A hyphen represents a miss. Is this pattern random? Or does it show non-random streaks of successful shots? Most people see patterns, And some would even argue there are patterns and could tell you exactly some way that the patterns exist. However, the data were generated randomly. Each spot had a 50% chance of being an X and a 50% chance of being a hyphen, without taking into consideration previous shots. So, why do we see clusters? Perhaps it's because our brains have evolved to find patterns and are actually really good at it. This ability may have served our ancestors to avoid predators and poisonous plants, but we must recognize this built-in mental bias. Statistical rigor is essential to avoid being fooled by apparent patterns among random data, just like the pattern that you probably see here that doesn't exist. What about variability, particularly within small populations? Well, let's look at an example related to age-adjusted per capita incidence of kidney cancer. This is a fairly rare cancer with an incidence of about 15 cases per 100,000 adults in the United States. In data collected in 1998 by Dr. Gelman, counties with the lowest per capita incidence of kidney cancer were mostly counties with small populations. One could imagine that environment in these rural counties leads to lower rates of kidney cancer. Sort of makes sense. However, the counties with the highest incidence of kidney cancers also tended to be the smallest populated counties. Why? One might imagine that lack of medical care in these tiny counties leads to higher rates of kidney cancer, or you can imagine several environmental aspects leading to this. But isn't it strange that both the highest and lowest incidence of kidney cancer are in small population counties? The reason is actually quite simple. In large counties, there's little variation around the average rate. Among small counties, however, there is much more variability. Consider an extreme example of a tiny county with 1,000 residents. If there are 0 cases of kidney cancer, then this county would have the lowest incidence, as shown at the very top. However, in that same county, if only one person has kidney cancer, then that county has the highest incidence. So, a pretty big swing from just one case. Compare this to the counties with more residents, as outlined here on the slide. So counties with small populations have both lower and higher incidences of cancer rates because there is more random variation within small groups than you see within larger groups. This simple principle is logical, yet it is not intuitive to many people. Many people expect statistical calculations to yield definitive conclusions. Look at this example. If you compare the number of people who died by becoming tangled in bed sheets with the per capita cheese consumption, we find an actual statistically significant correlation. The correlation, in fact, is the R value is 0.947, which means that there's a 94% correlation between these two data points, between the two variables. The data come from the USDA and the Centers for Disease Control and Prevention. But the real question is, do we really think that there's a relationship between dying by bedsheet and cheese consumption? No, this is what we call a spurious correlation, where there is either coincidence or a third related variable that's unknown that leads to the mathematical correlation. But it's important to note that there is no causal relationship between these two variables. Correlation does not mean causation. Each statistical conclusion is stated in terms of probability, and understanding statistics and how to interpret them can be difficult if you keep looking for definitive conclusions. Our brains do a really bad job of interpreting data alone. We see patterns in random data. We tend to be overconfident in our conclusions, and we mangle interpretations that involve combining probabilities and looking at unrelated variables and correlation analyses. Our intuition leads us astray, and that is why we need statistical rigor to avoid reaching invalid conclusions.